Get going. Welcome everybody. We have really excited that we have Bob Galyen, who's going to give us a talk and answer questions on the complex world of batteries. Bob's been a great friend to the company and an advisor now for many years, and is one of the absolute leading experts on batteries and EVs. And over to you, Bob, and thank you for doing this.
Oh, you're welcome, Oliver. And thanks, Holly, for setting this up. Yeah, for everyone that's on the call, if you don't know me, I would hope I get a chance to meet you next week at the Battery Show. Next week is the largest conference in North America for the trade association, if you will, for batteries, and that's hosted by Informa Markets. So I'll be there as the chairman for the 15th straight year. So this thing has grown to over 20,000 people that attend now. So I'm looking forward to meeting anyone that's on the call there. And also I've saved about 30 minutes of conversation at the end of my presentation, because one of the things I get the most of is, please give me some access to ask questions, Bob, because we really like to be able to have somebody that's done it before give us some advice. So with that, let's go ahead and get started. I'll got to get the mouse on the right screen so I can advance the screen. So with great humility, I show this slide because 2 years ago this month, Oliver, I did a webinar for you guys. And this slide was in there except for the narrative that's on the left. The guy that's on the far right is Dr. John Goodenough, and God rest his soul. He was a brilliant, brilliant scientist, and I was honored to give him a prestigious Pioneers Medallion from NAATBatt International. But just last February and again in June, I had two near-life threatening events in my lifetime that I almost joined John on the other side. But I'm thankful to be with all of you today, because it was a very humbling period of time, and I'm very thankful that God gave me a chance to stay with everybody that's on the call today. So let's go ahead and move on forward, because this is quite an exciting opportunity for me to help Oliver and the team, and maybe to help educate and train some folks. So I used this slide a couple of weeks back ago when I was at the University of Alabama, and they have started a new center called the AMP Center, which is a really remarkable organization down there in Alabama. It's probably next to our national labs, probably one of the greatest natural, or one of the most important resources that we have in the United States outside of our national laboratories. But this slide is about securing basic battery building blocks. And what that means is, for those people that are on the call today that are not battery experts, because many times we have people joining that are either out of the investment community or supply chain networks, maybe don't understand the basic battery building blocks. But I'm going to just go through these very quickly. First of all, you can't build a battery without an anode. An anode is what we call the negative electrode. And that means that we build this particular type of a part of the cell that makes up the battery, that typically is made out of graphite, silicon, put onto a copper foil with some binder and water to make the anode. And then on the cathode side, which is the one that's probably most important to us talking today, is the things that go on to that is a composition of lithium iron phosphate, which is composed of lithium and a hexafluorophosphate material. And then there's a different type of material called NMC, which is one that's really important to us for discussion today, because nickel, manganese, and cobalt are typically very precious metals and very expensive metals. But we're going to see today that that is a primary objective of what we're trying to do with the ocean bed harvesting of these nodules. And then we put that onto an aluminum foil with some binder and some carbon, and typically put together with a nickel or with an NMP solvent that then we have to vaporize and take off and recover. But the next component is the separator. The separator is basically a material that goes between the anode and cathode to keep them from shorting out, because each of these cathodes and anodes are about a 3.5 to 4 volt potential difference that would cause chaos if those two come into contact with each other. But these separators consist of typically a polyolefin coated with a binder and a highly purified aluminum material that makes the separator and prevents it from shorting out. And then the electrolyte system is typically made up of a salt, a solvent, and some additives for long-term stability in terms of life expectancy, and low temperature performance, high temperature performance, and longevity of the battery. And then, of course, we got to put all this stuff into a package. And this package is typically something like a prismatic can with a lid on it, or it could be a pouch, which is an aluminum material that is coated with a polymer. And the third one is a cylindrical type of cell that is a round, typically can with a lid on it. And as an example, the prismatic cells that are used in a BMW car, pouch cells, you can find those in a Nissan Leaf or into a General Motors EV type of product. And also cylindrical cells are used in typically Teslas. So each one of these different packaging forms are typically a bias of engineering principles for each one of the companies. But regardless of what the packaging is, it's the stuff that's above the packaging that I mentioned, the anode, the cathode, and the electrolyte system separator is what's really important to us. But moving past that is the manufacturing technology. And this was where the United States has been left in the dust by China. We are struggling trying to get the manufacturing technology in the United States. And regardless of which side of the aisle you sit on in the House or the Senate, manufacturing technology is a critical component of making batteries today that we lack, and we're trying desperately to get formed up here in the United States. Now, I used some of these pictures in my slides 2 years ago, and these are almost immutable because these are applications. And at that time, I likened it to a Rubik's Cube of applications that batteries can be used in. And there's hardly a device that we touch today that isn't powered by a battery of some type. And we see that this whole new era of innovation and invention and creating of applications are all reliable on dispatchable energy of some type. And what I mean by dispatchable energy, it can be stored into a device and can be put into that device and either moved or be put into a stationary position. So we see all these new kind of machines like eVTOLs, fixed wing aircraft are being electrified, even backhoes. Literally 7 years ago, that little backhoe in the left-hand corner, I got to drive that little rascal, and then I got to drive his big brother, the 22-ton backhoe. So all these machines exist today, and we see a big resurgence in energy storage, and I'll talk a little bit more about that later. But it's clear that batteries are something that the world relies on heavily today in so many different applications. Now, my old buddy, Roland Berger, Wolfgang is an interesting character, but he and I talk to each other about every quarter. But this one is one that he put together specifically to address the 2030 global market. And you can see that this global battery demand is accelerating almost in an exponential way. And you can see that by the year 2030, we're going to be approaching approximately 5 terawatts of battery needs. And possibly by the year 2040, I think these are maybe a little underestimated. We're probably going to be closer to 10 terawatts of energy storage demands for battery technology. But the important point on this chart, if you look closely at the blue part of the pie chart, nickel rich, roughly 51% by the year 2030, that's the one we want to focus on because that's part of the dilemma that the world faces today. They just can't mine enough nickel ore to get there, but in harvesting nodules off the ocean bed floor, it will easily get there. And you can see that possibly there will be more of a cost equality, if you will, or an equal cost between iron rich, which is typically lithium iron phosphate, and nickel, manganese, cobalt batteries, that we will reach a point of equity in terms of pricing. Then it's a matter of the application requirements that will drive which one of the chemistries will go into the battery. Now, I got this chart from my old buddy Wu Kai at CATL. He is the chief science officer. But there's one important point about this chart. New technologies are going to be absorbed into the market. It doesn't matter what goes into making these batteries. What we're finding is that every battery that's being produced is being sucked into the marketplace and put into an application. I don't care if it's that 160 watt hours per kilogram sodium ion battery, or whether that's a high energy density condensed matter battery at 500 watt hours per kilogram. The important point of this chart is that almost every battery technology that meets the rigors of the requirements of an application that have been properly verified through validation testing is being put into the marketplace. We still see a continuation of growth even in the lead acid battery market of a roughly 1% to 2% growth annual increase in needs each year. So almost every battery technology we see in the marketplace today is continuing to grow. Now, one of the key things is understanding history. Now, one of the most important slides in the slide deck today is this one, and it's what are the lessons that old Bob learned from China's success? Now, this is really an important point. Through all the years of experience, and 48 years going on 49 now, one of the key things that I found, and particularly when I worked in China at the CATL, was government support. That government support offers funding, infrastructure, and regulatory guidance to nurture and protect innovation efforts within industries. And I see that as where we were lacking in the United States in a big way. We are now starting to wake up to the fact that we do need some of these precious metals and stuff, and the government is starting to look at regulatory guidance and possibly going to help us in the future. The second key point was private equity investment. And in all my consulting work I've done in the last 5 years since leaving and retiring from CATL, is that we have a heck of a time getting money out of private equity because people want faster returns than what the battery industry can offer. And this, unfortunately, with the absence of private equity, this slows down our business growth by limiting how much money people have to spend on new projects that can help innovate and put the United States back in the game where China has given us taken away our lunch. The third key element of innovative success is available technology itself. When I worked in China, the technology was already there. When I got there in 2012, it was remarkable that they were already building lots and lots of batteries, but they were for consumer electronic products. The thing that surprised me there was it was just a matter of scaling. Well, when you say it's a matter of scaling, going from kilowatt hours to gigawatt hours is not a simple task. So putting that into play was a huge effort. Then the fourth thing is what I usually call the M&Ms, the man and the machine. And here I've restated it as human-machine collaboration, because with the advent of artificial intelligence, we're now not only seeing the education and training of the human beings, but the education and training of the machines through machine learning. This type of collaboration boosts productivity, sharpens decision-making, and inspires creative problem solving. And we see that happening, particularly in China right now, because they're ahead of us so far that they're already implementing the AI into the machine design itself. Now, moving on to something that's really important is who is the dominant supplier of these raw materials that we need to build batteries. And this is an excellent chart that shows very clearly that China is leading the world in terms of production of most of the minerals that are needed to make the battery technologies. And in comparison to these different materials, such as the copper, nickel, cobalt, rare earth materials from rare earth magnets, and manganese, we look at the far right at oil and use that as a comparison. So, we've got United States and China and the Saudi Arabian contribution to oil. We look at the raw materials for making batteries. Many people in the Middle East now are looking at these raw materials as the new oil, if you will. It's pretty impressive when you talk to the people in the United Arab Emirates, Saudi Arabia, and others that, oh my gosh, one day oil may get rooted out by electrified products, and we need to be a part of that. So when you talk to them, they're really anxious and interested in talking about how they can get into these different raw material games. So it's a really important point on what the percentages are of these different materials, because with the kind of work that Impossible Metals is doing, this will change and maybe change dramatically forever once we get a responsible way of recovering the nodules off the ocean bed floor. Now, in the complex world of critical materials in global trade, there's some key elements of success here. And this is one that I use with several different government presentations that I've done, and many questions come out of this. But clearly, geopolitical cannot be ignored. The kind of things that are going on right now between China and the United States with the tariff wars that are going on in other countries around the world, there's no question that geopolitical issues cannot be ignored because it is changing GDPs of some countries in a different way. The second key point is permitting. It's almost impossible to get a permit to do a mine in less than 10 to 15 years, almost all over the world, with the exception of maybe Africa. But this is a critical point because governments around the world are trying to figure out how to accelerate and make permitting easier. Mining and harvesting, I think, are a critical combination here. Typically, I look at mining as something that requires a removal of some part of Mother Earth to get the product, and harvesting is simply removing it without disturbing the surrounding. So if we look very carefully at what Impossible Metals is doing, they're on the harvesting side, not on the mining side. And I can say it with great respect because I want to protect our environment. I've got degrees in chemistry and biology, so I can say unequivocally that what Impossible Metals is doing is the cleanest and most environmentally friendly technology that I've seen around the world. Transporting is a critical one. And I met with the government folks down in Alabama here a couple of weeks ago. One of the things that was key in that state is they've got deep sea capabilities in the port of Mobile, Alabama. It can take up to a 50-foot draft, so that means it can get any ship in the world into their port and offload it. They've also got an extensive rail system. They've got an extensive transportation in the highway system through great highways that go through that state. So when I look at the complex world of making battery materials work, I look at how things move around because transport is a critical part of that, and reducing the amount of transportation costs is absolutely essential. Another key point is processing. Many countries around the world do not have processing capabilities, and that's why China is carrying the load right now on battery technology, because back 30 years ago, the entire world took their requirements for consumer electronic products to China. China fast discovered to make consumer electronic products, they needed to have batteries. And to have batteries, they needed raw materials. To have raw materials, you need to have processing. So that's one of the reasons China has worked so hard over the last 30 years in creating processing, is that they knew they had to have those raw materials to make the batteries in the first place. Now, another key point is converting. You may be able to take all those raw ores and convert them down to the basic metals, but then you got to take those metals and put them back together and create something valuable, or the material into something that can be converted into something that's useful in making the battery. So it's really important to know when you get the raw materials that you have a way of taking it and building something like a nickel, manganese, cobalt, different variations, whether it's a 623 and 811, or different ratios of the nickel, manganese, and the cobalt. Not dissimilar to what you need to make the lithium iron phosphate, including the phosphate, iron phosphate, and the lithium, put them together to make the lithium iron phosphate. Then you need somehow to implement those materials. Once you've taken them and put them into some new form, you have to go and have to take these raw materials. An example again is a cathode, where you take a nickel, manganese, cobalt, have to put it into a slurry mix, put it onto a foil, and then build it into a cell, and then go out and market it and put it into a product in the field. So there's a cascading sequence of events that must occur in the implementation of these raw materials once you've got them under your belt. And then another key thing is that you build and design products that you can recycle. Make that somewhat like the lead acid industry, where over 99% of the lead acid battery is recyclable. Today, we're approaching 80-some% or higher in recycling a lithium battery, but it's still not quite there yet. But many people predict that recycling in the future is going to be absolutely critical to support the fast growth and rise of all the batteries that we need in the world today, because just the regular support of getting the materials from Mother Earth, it takes time, and it takes a long time to build up the materials to the point where you get recycling becoming a significant contributor to the overall recovery of those raw materials. And then there's an economic drive, and you'll see through other parts of the presentation today, the amount of money that's going to be spent on these raw materials, the amount of money spent on the recovery and expense of putting in capital equipment to recover these minerals and to recycle them and implement them is staggering. It's a really big number. And then I wanted to bring up this slide that I used 2 years ago. Again, I bring this back because these top 3 challenges really haven't changed. And this is something that was put together by the LiBridge Initiative. And I was on team number 1, which is the technology group. And these three challenges came up from all 6 of the teams that we established inside Lightbridge. And these challenges, I just want to go through briefly, is a lack of attractive returns on U.S. capital investment. As I mentioned earlier, people like to get a fast return on their investment in the United States. They want a fast turn and get margins up in the 10+% or even higher range in order for them to get the recovery of money as fast as they'd like. In China, it's a little different story because the people there think in a different scope, if you will, in terms of time frame. They think in terms of decades. We think of it less than months, I think, in a return on investment and capital. The second key thing is in the challenge is lengthy and uncertain timelines to secure permits and project approval, especially upstream projects. And again, this gets back to what I mentioned earlier about getting permits for doing terrestrial mining. There's a whole new opportunity in the world of underwater permitting and processing. It's my understanding, and Oliver can chime in later, that nations, sovereign nations, can mine within a 200-mile line of their shoreline, but anything past that requires a permit from the United Nations, who is the securing entity that gives you those permits. And then the third is a lack of access to energy raw material supply. Today, we're looking at a huge build out of new battery plants here in the United States. And those battery manufacturing plants don't even have raw materials that can be supplied from the US because we have no raw material suppliers to hit the quantities that we need here in the US. So what do? They have to buy the raw materials from offshore and bring them in and pay exorbitant prices for shipping and transportation, and sometimes on an increase on tariffs. Now we move into another segment of the presentation where the rise of lithium-ion battery dominance is well established, and you see here in this chart. When I went to China in 2012, we were just literally making megawatt hours of batteries. By the year 2015, when the bus market kicked in, China started growing very rapidly, and then the car started kicking in around 2017. Then it grew like wildfire, and you can see here that China has a huge dominance in the supply chain, if you will, of batteries. North America is lagging behind significantly, and so is Europe. Asian Pacific Rim, excluding China, has grown a little faster than the other countries around the world. But we're seeing growth no matter what in all countries around the world on electrification. But yet the United States is now taking a little bit of a back seat in terms of the importance of electrification of automobiles. Now we look at the total addressable market around the world in a commodity market where the lowest cost producers win. And as stated here, you can find these prices on the LME. But if you look in the lower left corner of the metals that we're looking at in terms of growth in the next 7 years, is roughly a 7% compounded annual growth rate. One of the big winners here is copper, and these nodules are laden with copper as well as nickel, cobalt, manganese, and therefore this is the big incentive for us to go after these different metals. And the chart on the right shows the different types of products that are being made around the world, and of all these different metals that are being used in producing products of metal types. Batteries are now coming up to 15% of the world market in terms of cost, or cost of spent, I should say. Pardon me. But one of the well-founded points that I'm trying to make here is these nodules are well suited for battery metal needs. And this is an interesting chart that was put together a couple years ago showing these polymetallic nodules that are on the ocean bed floor that companies like Impossible Metals are trying to harvest, is getting those things processed and create the basic metals that then go into be built into the types of metals that go into a battery. So one example here is the electric car showing a 75 kilowatt hour battery with an NMC 811 chemistry can have up to 53 kilograms of copper, 56 kilograms of nickel, 7.1 kilograms of cobalt, and 6.6 kilograms of manganese. That would cost a fortune if you had to do it off of terrestrial-based mining like they're doing today. So the cost driver for this, being able to extract these nodules and process them and get them built into battery materials, is an extremely importance to people like myself and other scientists around the world who want to make a more cost-effective battery. Now, if you look at the value of these metals per ton of the polymetallic nodules from different parts of the world, you can see here from the Clapperton-Clipperton zone versus the Indian Ocean versus Cook Islands, these polymetallic nodules are typically based on how much of the metals that are being burped out of these fissures, if you will, from the volcanic activities in the ocean bed floors. Because as these fissures release these metals into the salt water and they dissolve, then they become recombined, and these polymetallic nodules on the ocean bed floor have different percentages of composition. So it depends on where you're at in the world of how much of the material that you're going to get from doing these kind of resource recoveries off the ocean bed floor. Now, the nodule composition is also well suited for infrastructure, and particularly for defense and energy transition in general. So you can look at these different types of materials and the types of use of these different metals, such as the nickel that you can get out of these nodules, not only for electric vehicle batteries, but it can also be used in other products like the stainless steel, wind turbine blades, different types of alloys, critical defense products. Cobalt can be used for a variety of different things, such as chemical petroleum catalysts, paint and varnishes, critical defense products, hydrogen catalysis and fuel cells, manganese, another critical mineral in steel production. I used to do a lot of analysis for manganese and steel in my younger years, and this is also part of the critical defense production. Manganese silicates, a byproduct used in steel making as an example. And copper is the third most used metal globally, and it's used particularly for grid and distribution of electricity around the world, as well as in home appliances, building and construction, critical defense production, and data centers are being powered by different types of copper wires and things like that. So these metals are really important, and they're heavily laden in the use today in these different applications. Now, I picked 6 different megatrends in the global battery sector that I think are important to talk about, but just very briefly. The rapid EV adoption and electrification of transportation continues around the world. Now, it has slacked off in the United States, but it is still growing rapidly in many other segments of the world. The second megatrend is expansion of renewable energy for grid resilience. Almost every country around the world that has an old grid system like the United States is leaning heavily now on battery storage to have the opportunity to get more batteries into the grid network that can support the dilapidated grid, and the opportunity for increasing the production of electricity. Third is supply chain diversification and localization efforts. That is US and EU initiatives. That gets back to the point I made earlier, that if you can get the ore or get the materials in the local areas, you can get the cost down quite a bit by getting localization efforts in place so that you don't have to pay such a high cost in shipping and transportation. The fourth megatrend is sustainability focus. That is including the ethical sourcing of materials. You can almost count that the horrific things that were going on in the world and trying to secure cobalt has been nixed dramatically. And then another part of sustainability is recycling of critical minerals. As the CTO of NAATBatt, I recognize that we've got a minimum of 12, if not 13, recycling companies here in the United States. Now, whether all of them will survive or not, that remains to be seen. But clearly, sustainability focus is there, and that recycling is a critical part of that megatrend. Trend number 5 is one that I've just added within the last month or two, because in talking with large corporations that are getting into data centers and AI centers, like Amazon, like Google, other Apple and Microsoft and others, we're seeing that there's a need for plowing new grounds into market leadership, because there's a bifurcation of implementation, if you will, of battery technology into these AI data centers data centers and AI centers, because some people think that there's a right approach is using a high power density battery to put into an AI center versus that of a longer term or longer duration data center, where you have a larger cell energy format that you put into large data center storage rather than a fast and furious support of an AI center with a smaller, higher power battery. Now, one of the key things that I mentioned earlier about the isolation and purification of metals, there's companies like that of ReElement that Impossible Metals is now looking at as possible a project that would allow them to secure these raw materials, both from mining the materials off the ocean bed floor or harvesting the materials off the ocean bed floor, and using a technology like the one that ReElement does, which is a chromatographic separation. This is a large industrial grade type of chromatographic separation, which I really admire a lot and want to work with the ReElement people on the project to make these elements become a reality for the Impossible Metals Group. It's a very key point. Now, along the EV supply chain, if you want to focus just on EVs for a moment, you can see here how this plays out between mining and collection, chemical processing or extraction and refining and creation of the cathode, and then the cell production, the cell companies, and then finally the car production companies. This EV supply chain is really become well established, and now we're looking at just doing nothing more than scaling and getting bigger with new technology and implementation by these different companies. Now, my final slide here is kind of a renewal, if you will, of a creation of a new growth in our global battery trade in critical minerals. And I just wanted to finish up here with just a couple of comments that deep sea harvesting is really critical to our future. Companies like Impossible Metals will do this, such as a simple Department of Defense National Defense Stockpile requirement is an example of one of those deep sea harvesting solutions that the U.S. government is now supporting. Another simple one is new technologies like the one I just mentioned. ReElement is breeding new opportunities and cleaner elements that can help supply a more cost-effective element that goes into building active materials for batteries. And third is leverage state resources that different states in the United States might have. I'll be speaking about lithium at Arkansas at the end of this month under the respectful request of Governor Sarah Huckabee Sanders. Graphite is a big thing for a state like Alabama. Shipping and transportation is important to all states, but I live in Indiana, which is considered the crossroads of America. But then industrial contributions are really important because we don't really have the material, if you will, for building the industrial base yet, but we're getting closer. We don't have machines built in the United States that can make batteries for us, so we got to get that built up. And fifth is academic support. Education and training our young workforce, as well as our scientists, engineers in the future, is going to be critical for the future of the United States and other countries around the world. So with that, Oliver and Holly, I'm going to leave it up to you to let you police the questions coming in from the audience and see if we can spend a little bit of time addressing those questions as we can. Thank you for your attention.
Yeah, no, thank you, Bob. This was really fascinating, a great update. So if anybody would like to ask questions, the preferred route is to use the raised hand icon, which is at the bottom of the screen next to the red hang up button. And then in the order you raise your hand, we will take questions. Or alternatively, you can also type them into the chat. So maybe, Bob, I'll start as we are kind of waiting for some questions to come in. You know, we hear from a lot of environmentalist groups that the iron-based chemistries, the LFP, are going to take over 100% of the market and displace the need for any nickel and cobalt. What's your view on that?
Well, I don't think that's going to happen for several reasons. First and foremost, there's applications that's going to need the higher power material, as well as as the cost of those materials, the nickel, manganese, and cobalt, come down, there have been significant improvements in safety design of the cells that allow us to use these higher powered active materials in a safe and effective way, that we don't have to worry any longer about the horrific fires that we've seen in the past with these. There's actually some new developments in the electrolyte world, and a company just right out of the gate, Linova, as an example of that. They have a electrolyte that is flammable. When they did their first nail penetration test, the guys were standing right next to the cell, and I'm going, "These guys ought to move because they're going to get hurt." When they did the nail penetration test, nothing happened. It had no more than a 3 degrees centigrade rise. So we know that new technology is being developed across the plethora of different application needs. But as we find that these flammable electrolyte systems can be developed, nickel, manganese, cobalt can be as safe as a lithium iron phosphate. So I think that's a really good question. Thanks, Oliver.
Great. Kieran, please ask your question.
Can you hear me? Okay.
Yes.
Okay, thank you. Hi, Bob. Thank you for a very comprehensive presentation, a lot of information. I have been following the role of nuclear energy in the upcoming energy scene in the country. And what I'm learning there, that for nuclear power, it is very difficult to change the level of the power within the time frame of 10 to 15 minutes, because you have to move the control rods, and only France is doing that sort of thing. Mm-hmm. And there is some discussion on the general subject of providing large-scale, utility-scale batteries for the nuclear power. And as you know, the latest report, which came out a week ago or so from Bank of America, they are talking about up to $10 trillion worth of investment in a nuclear energy-related investment. And I then was wondering, to your, group of discussion there, has there been any interest in application of large-scale batteries for nuclear power stations?
Absolutely. There are talks going on with major corporations that are planning on supporting that, but it hasn't been made very public because a lot of concern over people thinking that nuclear is bad. Okay. I think nuclear is probably one of the best and cleanest and most effective types of energy generation that we can install. But you're absolutely right. It takes some period of time for ramping up and ramping down nuclear reactors. And what do you do to help supplement that type of ramp up and ramp down of a nuclear reactor? Batteries is a really good solution for that. And you don't want to waste all that energy and blow it off with steam if you're ramping it down, nor do you want to waste the opportunity, if you will, of having a blackout while you ramp up the nuclear reactor if there's a big demand all of a sudden. So you spread that load over the battery system while you scale up the nuclear reactor in some cases. So that's a very good question. It is a new usage, and it hasn't been talked about very much. And the reason it hasn't been talked about is many people in the world think nuclear reactors are bad. Okay, so good question. Thank you for asking.
Thanks for your input, Bob.
Yeah. Alexei, please ask your question.
Hi, everyone. I just have a question regarding the supply chain, the slide that I saw. What role section of the supply chain in possible metals are thinking? Are you going to be on the mining, harvesting side, or are you also thinking about doing the chemical processing and getting the precursor materials to the producers?
Yeah, let me answer that. So we want to go as far as delivering the high quality battery metals, the nickel sulfate, cobalt sulfate, manganese sulfate, but we don't want to be building our own mineral processing facilities. So what's normal in the industry is to work on what's called a tolling relationship, where we would deliver the nodules, the ore, to a processing plant on land, and they would then process the metals into the high quality that could be used as a precursor for the cathode, and that would then be delivered directly to our customer, and we would pay a tollage fee for every ton of nodules that was converted into these battery quality metals.
Thank you.
Rachel.
Hello. I was listening to some ongoing challenges regarding the deep sea mining, and permissions, it seems to be a rather large obstacle. I was recently reading that India has had grants from the ISA, like permissions, to harvest the nodules from the bottom of their ocean beds. And so why haven't other countries who have the nodules at the bottom of the sea floor, like Nauru and additional countries, and TMC to get permissions for the Charion Clipper Zone to harvest, as India has got permissions to be harvesting the nodules, whereas some companies do require to be sponsored from the country. However, Nauru should have the right to harvest the nodules around their ocean seafloor, whereas because India has got permission now, so deep sea mining, it is something that's being granted.
So let me clarify. So I think what you're referring to is the recent exploration award that India received from the ISA. But the thing to understand is that this is in the Indian Ocean, but it is not in the Indian exclusive economic zone. So it is in an area beyond national jurisdiction, the high seas, and hence the ISA is involved in permitting. If, and India does have deep sea minerals within their exclusive economic zone, then they do not require the ISA or any other jurisdiction. And that is the case with, say, the Cook Islands, with Japan, and for instance, the US and their activities in American Samoa. So there are two regulatory frameworks for deep sea minerals. It's within the exclusive economic zone of a country, typically 200 nautical miles off the coast of the country. Then it's treated as if it was on land. It's exclusively regulated by the country. If it is beyond 200 nautical miles, it's in international, and now the ISA is the regulator. But the US now has passed, historically has passed a law that says that it can also regulate in international waters.
Mm-hmm. Thank you.
Do we have any other questions?
Oliver, we have a couple in the chat.
Great.
Do you want me to go ahead and read them?
Yeah, why don't you read them out?
So the first one's from Andrew Thaler. Thank you, really interesting talk. What do you make of the recent Colorado School of Mines study that suggests the U.S. could meet its projected critical mineral needs through recovery from tailings at existing mines?
Well, I'm not an expert, Holly, in tailings of mines, but there are significant tailings out there. The question is, what percentage of the mineral that they're trying to recover from the tailings would be able to be processed in a cost-effective way? It's going to be really difficult for the tailings that where they were going after the primary ore in the first place to produce enough material, whereas the nodules are so rich in the minerals that you're looking for, and they're so much more cost-effective to harvest the minerals out of those nodules because they're in a very pure form in those nodules. There's not a lot of other stuff in there. Now, some of the nodules do have some rare earth metals and some other materials in there, but the effectiveness is, I think, going to outweigh that of what you can try to do in the mining tailings.
Let me add a little bit. I completely agree. I mean, I think fundamentally what we're confusing is the difference between a resource and a reserve. And so I put a link to a blog post that I recently wrote. So just for clarity, a resource is a mineral deposit. It could be tailings, which is the waste product from old mines, or it could be new deposits. But it's just the material exists. A reserve is material that is economic to extract, and you have permissions and you have technology to process. And so what we care about is reserves. going to Bob's point, it may be that there are parts per million in the tailings waste, but it would cost you 10 times the cost of getting them from the deep sea. Well, that isn't a reserve because it's just not economic. And so it may be that there is material, and I'm sure there is, but remember, this is waste material. A mining company has previously decided it was uneconomic to extract this. Now, with changes in technology and pricing, it may make sense, and it will make sense, to go back to some of that material and see what is now economic. But will that displace the need for deep sea minerals? Absolutely not. It's all about the cost. And ultimately, deep sea minerals have massive advantages on cost because their grades are up to 10 times higher than what we find on land. We have 4 metals in one, and we don't have to build a lot of infrastructure. We reuse ships and ports. So I think it's an interesting academic paper, but at the end of the day, it's reserves that matter, not resources.
Mm-hmm.
Great. All right. We have another question from Nora. Please speak to the education and training needed to create a long-term sustainable pipeline for this workforce.
Well, I'm going to reference the work that we're doing inside NAATBatt, where we have an entire committee that's working on this. This is at the top of everyone's mind. In fact, I don't see a copy of the. I just authored a book this last May, and it just came out on publication to address exactly this point. I had some of the finest battery guys in the world help write the book, and it was forwarded by Dr. Stan Whittingham, our Nobel laureate in lithium batteries, because we all recognize how important it is to educate and train our young workforce. That book was written specifically for scientists and engineers to get off and running quickly. But one of the key things that organizations like Alabama, I should have put it in my slide deck, they showed me the most impressive slide, and the people who were on the panel that are people who are educating and training children from the kindergarten level all the way up through high school, then into the academic sector of universities. And that value chain of education is going all the way back to kindergarten level, is a remarkable feat by any state. And so Alabama has really got a great roadmap if you want to follow what they're doing all the way through the education system. So, you know, I think there's an equivalent here. You know, when I went to school 60 some years ago, they always trained us in that school to be careful handling gasoline. Don't light matches around gasoline. Why? It explodes, it burns, it can kill you, right? It can create very strong harm to you. Today, we not only have to train our young children about a gasoline, but now we have to teach them about electricity, because when you're talking about all these electronic devices that we got around home, like power battery driven screwdrivers, we've got electrified air compressors and all kinds of things like that. It's a great question, but not a simple answer. We got to start the academic training all the way from the kindergarten level, all the way through high school and then into college. So become a part of the solution by joining NAATBatt and joining their workforce development committee. We've got several hundred people in there, and it's headed up by people that work in the workforce development as professionals. So this is really a good question, and a key answer to that question is get involved.
Bob, I have another question whilst we're waiting. You know, a question on, you know, the timeline for kind of new cell chemistries. Like you almost every few weeks you hear about some breakthrough in a lab. What does it take to get them into an EV that we can drive?
Typically, the cadence on new technology is 7 to 10 years, Oliver. You know, I keep hearing about all these marvelous new technologies. That was my primary job when I was CTO at CATL, was screen and evaluate new technology, because I can guarantee you every week I had somebody that had the greatest solutions to sliced bread. And how many of those made it through the screening process? Very, very few. And many of those ideas or from good scientific principle may have not have been the primary solution, some of the ideas that they had instilled in those new concepts could be applied to existing product. So the research that was done by many of these research companies is all for naught. It's for good use in possibly triggering another idea that could take that idea and springboard it to the front of the line. But that's far and few between.
Great. Yeah. So we have a couple more minutes, and if anybody has any burning questions for Bob on batteries, I'm also happy to take any questions you have on impossible metals. Just let us know. Otherwise, I think we should wrap.
Well, Oliver and Holly, thank you very much for the opportunity to do another webinar. I do these because I think they're important for people to hear from someone that is experienced. And I'm fortunate because my son just laughs at me. He says, "You made more lead acid batteries than any human on the planet." In fact, I got to show you this before we get off. This is the original EV1 battery.
Oh, wow.
This is the casing. I took the lead out of it because I don't want to bring lead in the house, but this is the original J1797 package that we put into practice in SAE just so that we had Ford, General Motors, Honda, and Toyota that were members of that private, I'll call it private group, that wanted to design and build a battery they could all use in their electric vehicle development. So I think that's quite an interesting thing. But I really appreciate the opportunity to talk with a group of diverse people that join these webinars, because it not only opens my eyes, but it also gives me the opportunity to educate, train, and teach. Looks like Alexi's got a question.
Yeah, Alexi, please go ahead.
Just one more question to Robert. If you can elaborate more on the midstream process, how advanced the mid processing in United States. As you pointed, a few companies, Abbas, POSCO, Redwood, Unicorn, but they all looking for the precursors. And before they get to the precursor, you have to process the raw ore or nodules somehow and somewhere. So what's the development here in the United States on that area?
Well, I did mention that company ReElement, Alexi, for the fundamental reason that they break the material down to the basic element. Okay. Now, once you've got that basic element in a solution form, you can do whatever you want to. You can flip the anion on it, use it for making an NMC. You can take it and put it into the iron industry for making better steel. You can use it for electroplating. I mean, there's many needs of these ions once they have been broken down to their fundamental building blocks, and then you can do whatever you want to with them. As a chemist, I just love the fact that you can take these elements to just about any process and flip the ions on them and do whatever you want to do with those ions. But we don't have much processing capacity in this country today. There has not been an infrastructure built around creating what you just asked the question about. Okay. So that's an area, if you want to get into it, you can make a lot of money very fast. Okay.
Yeah, before getting into this area, this is why I ask, as I need to know.
Yeah, absolutely. This is a real key point, that if you get into this area, you can make a lot of money very quickly. But you got to be one of the front runners.
Mm-hmm. Well, thank you. I think we should wrap up there. Okay. Thank you again, Bob. Really appreciate you taking the time, and thanks the audience for asking some great questions. We will, as always, post this on the YouTube channel next week, and we will hopefully announce the November webinar in the next few weeks. So thank you, everybody, and that's a wrap.
Thank you very much, Oliver. Hope to see everyone at the Battery Show next week.